Hello everyone, in today's lecture we are going to discuss the floating point representation. So what floating point is? It is a decimal number. That means when we represent the number in decimal form, that is actually the floating point number. So we are taking one example, that is 1259.125. So every floating representation, that means every floating number consists of three parts. Okay. So first part of floating point number is mantissa. Second is base. Third is exponent. So these are the three parts of the floating point number. Okay. So how you will represent these three parts in this number? This number can be written as okay. So when we put three decimals here, the number will become the same. Okay. So we can represent this number, this decimal number. The decimal number always have the base of 10. So this number can be represented as this number. So in this number, this is called as mantissa and this is called base and this is called exponent. Okay. So according to IEEE, 754. Okay. That means IEEE 754 is a standard. It is a standard to represent the floating point number. Standard to represent the floating point number. Okay, so according to IEEE 754, the floating number can be represented in two ways. First is single precision format. First format is called as single precision. Second is called as double precision. Okay, in single precision, the floating point number is represented using 32 bits. Now as this double precision, the double is here. So in this double precision method, the floating point number is represented using 64 bits. Okay, so now we will discuss the format for single precision and double precision. Now this is the format for the single precision floating point number. The total length of the number will be 32 bits. So from 0 to 31, including 0 and 31, the total bits are here 32 bits. Okay, so here the leftmost side, here 1 bit is reserved to represent the sign of a number. Sign. Okay, the sign can be positive or negative. In the case of positive, the number will be, now if the sign is positive, that means the leftmost digit will be 0. If the sign is negative, that means the leftmost digit will be 1. Okay, so after that, here it is the exponent field. Exponent field. The length of exponent field is 8 bits. Okay, so 32 minus 8 minus 1 remaining bits are 23 bits. Okay, so 23 bits are used to represent the mantissa. Okay, so this is the basic representation of this floating point number using IEEE 754. Firstly, we will do the single precision floating point number. Okay, we will take one example here to tell how to convert the decimal number into single precision floating point number. Now basically in this step 1, what we have to do in this step 1, we have to convert the convert the given decimal number. Decimal number is a number having the base 10. Okay, so convert the decimal number into binary number. This is the first step to convert the given number into single precision floating point number. Decimal number into binary number. Okay, so binary number is a number consisting of zeros and ones. Okay, now here binary number will be having the base of 2. So now what is step 2? Step 2 is to normalize the number. Normalize the number. And what is step 3? Step 3 is to find the value of e, to find the value of exponent. Okay, so from the normalized number we will be able to find the value of mantissa. We are taking the example to convert a number into to convert decimal number into floating point number, that would be single precision. Okay, decimal number into single precision floating point number. Okay, so here we are taking one example. Suppose the number is 1259.125. Okay, so we have to convert this decimal number into binary number first. Okay, so step 1 is convert the given number, convert the decimal number into binary number. Okay, so here how you will convert this number into binary? So keep on multiplying to convert this decimal number into binary number. Keep on multiplying this number with 2 until the value is whole number. Okay, now here the value will be 0.250. After that again multiply it with 2 and the value will be 0.500. After that again multiply 0.500 into 2. The number will be 1.00. So here the number is whole number. Okay, so stop converting it into the binary number. The number is converted into binary here. So here the 0 comes, so the value of 1259 will be completed with step 1, and the value of 1259.125 in decimal is equal to 100,111.01011.001. Okay, move towards the step 2. So now what is step 2? Step 2 is to find the normalized value. To find the normalized value. Okay, normalized value. Yeah. There is one notation according to which we have to convert the number into normalized number, and that notation is 1.n to e minus 127. Okay, so we have to convert our number into this form. Okay, now here n is actually the normalized value. Normalized value, or you can say normalized number. Okay, So our number was okay. So we have to convert this number in this format. Okay. So just put one decimal before this. So just put one point after this one. Okay. That means the number will become 1.0011101101011 into how many places we have shifted to represent the decimal point here. The positions are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right here 2 raised to power n. Okay. So you can see that we have got the value according to this format 1.n. Here n is the normalized value, and this is will be equal to n. Okay. So now it's a turn of comparing two exponent e minus 127. Okay. So it will be equal to 2 raised to power 10. Now e minus 127 equals to 10, and we will get the value of e, that will be equal to 10 plus 127, and that value will be 137. Okay, so now e here is 137. Now we are going to perform the step 3. Okay, in step 1 we have converted the decimal number into binary number. In step 2 we have compared our number according to one format, that was n to e minus 127. Okay, so now in step 3 we have to 137. So now convert the value of e, convert value of e into binary form. Okay, so how you will convert this? Let me convert the number. 2, 8, 16, 1, then 1 will be the remainder here. Okay, so this will be the binary of 137. That means 137 in binary will be equal to 10110001. Okay, so this will be our exponent. So now what was the format of single precision floating point number? The format was total bits were 31. One bit was used to represent the sign. Okay, so the number that 1259.125 base 10. So this is a positive number. Okay, so here write the bit 0. Okay, here write the 0 because our number is positive. After that, second part, that is using the 8 bits. It represents the exponent. It is basically for exponent. So what our exponent is? Our exponent is 10110001, this value. Okay, this value. So this is already, I think, 8. 1, 2, 3, 4, 5, 6, 7, 8. So exponent here require 8 bits. Okay, so if there are not 8 bits in your exponent value, complete that 8 bits by writing 0 before mantissa is here. It is a position to show the mantissa. So whatever mantissa is, the normalized number will be our mantissa. Okay, so leave this one and write the mantissa value here. It is 001110110110001, not the 23 bits. Just count the bits. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you can write here dot dot dot. Okay, this is your basically mantissa. So this is your single precision floating point number. Finally, your decimal number, given decimal number, will be converted into this form. Okay, this is a floating point conversion, that is single precision.